Hi guys, so today we are going to be talking about periodicity and how you can use a periodic table to identify periodic trends. So the three trends that we are going to start out talking about are atomic radius, ionization energy, and electronegativity. So let's go ahead and start out with atomic radius. So atomic radius refers to how big an element is. So when you have an element, you have a nucleus, and in the nucleus you're going to have some protons and you're going to have some neutrons. Now, where are the electrons? The electrons are located in this thing called the electron cloud, and they're going to be scattered around this area. So what the atomic radius is, it's the distance from the center of the nucleus to the edge of the electron cloud. So when we learned about electron configurations, we know that in electron configurations, you're going to have energy levels. And we know that on the periodic table, each period represents an energy level. So as you go down an energy level, you're adding shells of electrons. So like Bohr's model, you have your nucleus and you're going to add shells of electrons until you fill all your electrons in. That's what's happening here. You're adding shells of electrons, so your atomic radius is going to be a lot bigger. Now you can see from this diagram that if you have your nucleus from here to one electron shell, you can tell that it's going to be a lot smaller than if you have a radius from here all the way to this outside shell. So naturally, your atomic radius is going to increase as you go down. Now, I know there's also a trend from left to right or from right to left, and I know that you may be thinking as you go from left to right that your atomic radius is actually going to increase because your atomic number is increasing, but that is actually not true. Because you're adding more protons each time, you're shrinking the element because protons are pulling in those outside electrons that are in that sea of electrons. So your atomic radius trend is going to be like this. It's going to increase from right to left, and it's going to increase from up to down. So your biggest element here would be francium. So now let's go ahead and talk about ionization energy. Ionization energy has a similar trend to atomic radius. The ionization energy is referring to how much energy is needed to take an electron away. So now that we have an understanding of which elements want electrons and which ones don't, so in case you need a refresher, the metals don't want electrons, they want to lose their electrons. The metals are going to form ions and lose their electrons to form a perfect octet, while the halogens and other nonmetals, they are going to want to gain electrons. So the metals over here, so in this area, they're going to have lower ionization energies because they want to lose electrons rather than gain electrons. So when we're looking at ionization energy, it's going to increase as you go this way. And also, ionization energy is also going to increase as you go from down to up. And that is because when you have shells of electrons, the electrons are further out, like in francium on the outside, and they have less desire. I guess you could say it's easier to take them off than as if they're held in really tight. So when we look at helium, helium only has 2 electrons. So it's going to be extremely difficult to take one away because it's held in that just one electron shell. Rather than radon over here with 86 electrons, it's going to be easier to take it away, but not as easy to take away as francium because francium is a metal and it wants to lose its electrons. Okay, so now we're going to talk about electronegativity, and it's kind of also a similar thing. Electronegativity is referring to how much something wants electrons, so its desire for electrons. So electronegativity, now you may be thinking also, what does it have to do with the metals? Electronegativity really doesn't have as much to do with the metals because they want to lose electrons again. So your electronegativity is going to be the same trend as ionization energy because it's going to increase as you go this way. So that's your electronegativity. And it's also going to increase as you go from down to up. Because the ones that have less shells are going to really want those electrons than the really big ones down here. So your most electronegative element, though, will be fluorine. And I know that seems confusing because you think helium has the highest ionization energy and fluorine has the highest electronegativity. But the noble gases are different. The noble gases are very different. because the noble gases already have those 8 electrons, they don't need any more. So hence their desire for electrons is not there because they already have 8 electrons. So even though they have very high ionization energies, they will have no electronegativity. So the most electronegative element you see will be fluorine, and fluorine is going to be a 4.0 electronegativity, which is extremely high. And also oxygen has a very high electronegativity at a 3.0. Okay, so now we're going to be talking about this idea of isoelectronic. And what isoelectronic really means is it has the same amount of electrons. Amount of electrons. So what exactly does that mean? Same amount of electrons. So when we look back at the periodic table, we know that elements have the ability to form ions. We know that elements, the metals, will form positive ions, and we know that the nonmetals will form negative ions. So we look here, we know that all these elements in this area are going to form positive ions. Now, what would they be isoelectronic with? Well, they would be isoelectronic with elements over here. So when you're comparing things that are isoelectronic, you're usually comparing ions with noble gases. So when we look in this area, we can see that chlorine here, chlorine ion is going to have a -1 charge. And when it has a -1 charge, it is forming an ion to be like argon. It's gaining an electron so it can have 18 electrons. So chlorine and argon are 2 examples of isoelectronic species. Now let's look over here. There's also isoelectronic metals. You can have metals that are isoelectronic things with chlorine and noble gases as well. So potassium is going to be isoelectronic with argon and chlorine because potassium loses an electron to be like argon, and when chlorine gains an electron, it is now also like argon, so all 3 of those are also isoelectronic. Now calcium will also be isoelectronic because it's losing 2 electrons. So now let's go back here. So when we look at isoelectronic species, there's also things that correlate with the atomic radius. So if we're looking at, let's say, calcium. So calcium, let's just draw a picture. Let's say calcium looks like this. So the atomic radius of calcium is about this big. Now, when we're looking at calcium ion is actually shrinking in size. And it's shrinking in size because it's losing electrons. When you're losing electrons, your protons are bringing in those elements closer into the center. So calcium ion would look like this. Now, noble gases aren't going to change because they don't form ions. So let's just say this is argon here. Now, if we look at chlorine, which is another isoelectronic species, let's just say chlorine looks like this. Now, when we form the chlorine ion, chlorine is going to look something like this. And opposite of the way that calcium performs, chlorine is going to be much larger because you're adding electrons. So when we're looking at isoelectronic elements, the noble gas is going to be relatively the same size. The ion, the negative ion, is going to get much larger, and the positive ion is going to be much smaller. Oops, that should be a 2 there. Let me change that. And also, if you're comparing elements to themselves, so if you're comparing calcium and calcium ion to each other and you say which one's bigger, well, you say calcium because calcium doesn't have those loss of 2 electrons that shrinks the element. So these 3 elements are examples of isoelectronic elements, and this is just a comparison of their sizes. All right, so now we are going to talk about reactivity. And similar to the way electronegativity is, reactivity is really only for metals. Non-metals are really not going to be very reactive, and noble gases are really not going to be reactive at all. So when we're talking about reactivity, we are mainly going to focus on metals. So when we're looking at metals, the reactivity trend is going to go this way. Your alkali metals are going to be your most reactive metals, and then your alkaline earth metals. Also, your reactivity is going to increase from the top to the bottom. And that's because the elements at the top, they're holding their electrons in really tight. And they don't have as many loose electrons that are going to be able to come off and react and cause a very big reaction. So when you look at elements like cesium and rubidium, those are going to be extremely reactive. And while lithium is still very reactive, it's not going to be as reactive as elements like rubidium and cesium. All right, so here are a few practice problems, and they are for each periodic trend that we talked about. So if you want to go ahead and pause the video, and then we can talk about the answers. All right, let's see how you did. So atomic radius from smallest to largest, that's going to be the calcium ion, because remember, calcium ions make very small elements. Then argon, phosphorus ion, it's going to be very big, and then krypton. Okay, ionization energy from smallest to largest. Okay, that's going to be francium, remember, lowest ionization energy, then magnesium, phosphorus, and then helium, which has the highest ionization energy. Electronegativity from smallest to largest. So actually, it's going to be right in that order because neon has, remember, it's a noble gas. It has no electronegativity at all. Then it's going to be rubidium, oxygen, and fluorine. And reactivity from smallest to largest. So krypton, because that's a noble gas. So really, it has no reactivity. Then nitrogen, very low reactivity. Then lithium's still very high reactivity, but not as high as rubidium. Okay, thanks for watching, and I hope to see you soon.